All right, let's look at a situation like this, and this really illustrates why calculus is so much better than what you could do before. We could do things like, if we had a spherical balloon, we could find the ratio of volume to radius and things like that before, but those are all static, right? Those are all going to be properties of a balloon that's not changing. Okay, but if the balloon is changing, let's say that we're blowing up the balloon by adding gas to the balloon at a fixed rate. Well, that's calculus, right? Because now we can actually explore the changes in the balloon, the rates of change of the balloon, which we recognize to be derivatives, right? So let's read this question here and see if we can come up with a way to at least start our exploration, right? So gas is being forced into a spherical balloon at a rate of 400 cubic feet per minute. Okay, what is it that we're trying to find? All right, we're trying to find at what rate is the radius growing when the radius is 10 feet. So first of all, let's even just try to figure out what quantity are we trying to find. At what rate is the radius growing? A rate is a derivative, right? Derivatives, we're going to take the derivative of a quantity with respect to something, though, right? We have to measure the rate with respect to something. Does that make sense? Like, for example, we could ask the question, how fast is the radius growing with respect to, something goofy like volume or something like that. But what do you suppose we're probably measuring it with respect to? What do we typically measure rates of change with respect to in the real world? We want to know how fast is something changing with time. Yeah, right? So what we're really looking for here then is the rate of change of radius with respect to time. And what we're going to see in physics and therefore in calculus too is that if we just talk about a rate and it's not explicitly telling us what it's changing with respect to, the implication is that it's time, because that's what it almost always is, right? So how would I say that as a derivative then? That's d what, d what? What's our variable for radius? R. What's our variable for time? So therefore, what's the derivative going to be? dr dt. Yeah, does that make sense? Or if we want to, we could say r prime of t if we wanted, right? Okay, so that's what we're looking for. What information are we given about this situation? Okay, we know they tell us how volume is related to radius. We probably already knew that. But they tell us some other stuff. They tell us that we want to know what dr dt is when the radius is 10 feet. So what's that telling us? It's giving us a value of what variable? Of r. Okay, so we're interested in one frame of a movie here, aren't we? Because this is something that's not static, it's dynamic, it's changing. So we're filming a balloon expanding as air is added to it, right? We're looking at the frame in the movie where r is 10, right? So that's one thing that we know right there. Okay, r is 10. It's that frame. What else do we know? They also tell us something up here. They say gas is being forced into a spherical balloon at a rate of 400 cubic feet per minute. Now the units are really useful here. We can use what's called dimensional analysis. Cubic feet per minute. Those are units of what divided by units of what?
Cubic feet divided by.
So cubic feet, those are units of what quantity? Volume. Right. They're units of volume divided by units of time. Okay. And it describes this as a rate, correct? So then what is that really telling us? That's telling us d what equals 400.
dV over dt.
dV dt. Very good. Okay. So we've been given some stuff here, haven't we? right? We're looking for dr dt, and we were given some other stuff, right? So step one of our solution is, what are the snapshot variables? The snapshot being, another way you can think about it, a snapshot, or you could even think about it as being the frame of a movie. So we're capturing that one frame is like a snapshot in an otherwise dynamic movie, right? What are the quantities we're given? Well, we're given that R is 10 feet, right? And we could even, if we wanted to, as long as we're going to be consistent with our units, we could even just kind of suppress the units. As long as we don't change our units. We're going to measure units of distance or length in feet and units of time in minutes. As long as we do that, we're okay. Now, what is this dot here? Okay, this is a shorthand I need to tell you about. Because we use time so much in physics, and calculus is really just a tool for physics, and other things too, but in this case, physics. Here's the notation that we're going to adopt. We're going to say that dv dt, we could also write as v prime of t, or you might think as v prime. Okay, sure, it is v prime, but because we're differentiating with respect to t, we're going to add some extra information here, and we're going to say, okay, instead of calling it a prime, we're going to call it a dot. So a dot always indicates that we're differentiating specifically with respect to t, okay? So we're going to change this prime into a dot to mean that it's the derivative of v with respect to time. How do you suppose we would say a second derivative with respect to time? Two dots, side by side, okay? So that summarizes this information right here. So let's kind of color code this. So our 400 cubic feet per minute is right there, right? And I added the units, but once again, we could even forget the units. The R equals 10 is right there, right? And then what we're looking for oops, I want to do that time. Just want to do that. What we're looking for is at what rate is the radius growing? So that's our R dot equals. Okay. So step one is we're just going to summarize everything. Summarize everything by identifying what the snapshot variables are. What are the values at that we're going to specify at that one frame in the movie. Okay? That make sense? Step one of our process. Okay? So let's look at step two. Step two is we've got to identify what we're going to call the parent equation. Okay? So if we were to blur our calculus vision here and ignore the dots, so we're ignoring any rates, what are the static quantities that are involved in this problem? So if we ignore the dots, it just looks like we've got V's and R's, right? So we want to find what is the equation that relates those static quantities. Usually it's going to be like maybe a geometry equation, or it's going to be maybe it's going to be some kind of a kinematics equation if we're dealing with a physics example, or who knows. It's going to depend on what the situation is specifically. But in this case, the equation is going to be volume of a sphere is related to radius by the equation v equals 4/3 pi r cubed. Okay, so that's what we call the parent equation. So we got to find that. Okay, step three is going to be to relate the rates. We're going to implicitly differentiate with respect to time, right? Because these are all rates with respect to time. So we're going to do this process that you've been practicing of implicit differentiation. Well, what do we get if we differentiate the right side with respect to t? Just get dv dt, right? Or v dot. Okay, that means dv dt, right? What about the other side? Well, now I got to use chain rule, right? I've got my 4/3 pi r cubed. I can leave the 4/3 pi out front because that's a constant. But what's going to be the derivative of r cubed with respect to t? At the outer layer, I've just got hand cubed, right? What's the derivative of hand cubed? What's the derivative of hand cubed? 3 hand squared. So I could take the 3 times the 4/3, cancels the 3 on the bottom, I just get a 4 pi. Then there's my r squared. But then if I look inside, well, what's behind my hand is actually an r. The derivative of r with respect to t is dr dt, or r dot. Okay, make sense? So now we've related the rates, all right? Well, what is it that we're trying to find? Okay, step 4 is we're just going to isolate the variable, whether it's a rate or a static variable, but it's probably going to be a rate because this is a related rates problem. We're interested in rates here. So we want to solve for r dot. So to solve for r dot, I'll just divide each side by everything that's being multiplied by r dot. So 4 pi r squared. And then I plug and chug. That's it. Okay, so the last step is just going to be plug and chug. So if I plug in all the values, the v dot is 400, the r is 10, and so I end up with 400 divided by 4 times pi times 10 squared, so 400 over 400 pi is just 1 over pi. And what would my units be? Remember we said we're going to do units of length are going to be in feet and time is in meters, and so r dot would be dr dt. So I'm going to have units of length, a radius, divided by units of time, and so the units would be feet per minute. Does that make sense? That's related rates. Okay, what do people do wrong on related rates problems? The big mistake on related rates problems is that sometimes people want to plug in values in step 2 before they differentiate. But that's a problem, isn't it? Because if I plug in values of these variables, then the variables start to look, instead of variables, look like what? Numbers or constants. And the derivative of a constant is 0, right? And so we can't do that. We can't plug in any specific snapshot variables until after we've differentiated to relate the rates. Then we can plug stuff in, right? But we have to differentiate first because we have to know dynamically how are these quantities changing with respect to each other. And they actually are variables, right? You can picture as the balloon grows, the volume and the radius are changing. They're not specific static quantities. We're going to ask, while it's changing, at that one frame in the movie, what is the rate at which r is changing? Okay, does that make sense? Okay, you find something kind of interesting here too. Look at this part. I just want to draw your attention to something I think is kind of interesting. Look at this part right here. Look at that equation. So how is r dot related to v dot? Right? So if we're pushing air into that balloon at a constant rate, then the rate at which the radius is changing is inversely proportional to r squared. So what's that tell you? The bigger the radius, as the radius gets bigger, what happens to the rate at which the radius of the balloon changes? If I'm pushing volume in at a constant rate, it's going to get a lot smaller, right? Have you ever experienced that before? When you're blowing up a balloon, it's very satisfying at first. A couple puffs and you get the balloon seems to be growing pretty rapidly. But have you ever noticed as the balloon gets a lot bigger, it really slows down, doesn't it? If the balloon's pretty large, it takes a lot of puffs to get that thing to be even remotely bigger, right? And the calculus gods are telling you that right there. That's the equation that dictates that. The bigger the radius, the slower that radius is going to increase for each puff, right? You see that? All right, so moving on down here. Now we want to know at what rate is the surface area growing when the radius is 10 feet. Okay, so now we're answering a different problem, right? We need different snapshot variables. Well, I think the radius part stayed the same, didn't it?
Yeah.
Right, so we've got the frame in the movie where r is still 10, v dot is still 400, right? But we're asking a different question. Now we're asking, at what rate is the surface area growing? So we're asking for, instead, we're asking for s dot, right? Does that make sense? I guess I didn't include that, I should have. Whoops, you might want to add that to your notes. So we're actually asking S dot equals what? But we do have one additional piece of information, right? From part one, we solved for R dot, so that might be helpful. So then what's going to be step 2?
Parent equation.
Parent equation. So what's the equation we're looking for? If we erase all the dots, we're looking for S, right? So S needs to be included, looking for S dot. So we need S to be included in our parent equation. It looks like we're going to have S's and R's and, well, maybe not a V in this case, right? There really isn't a convenient equation that includes V's, but there is one that includes S's and R's, right? Surface area equals 4 pi r squared, so that's our parent equation. Okay. How do we know that's a good one? Well, that's a good one because I have information about R dot and R, and I'm looking for S dot, right? So what do I do with the parent equation? Yeah, I'm going to implicitly differentiate with respect to time. So I'm going to relate the rates. So on the left side, what do I get if I differentiate with respect to t? But okay, on the left side here, I'm just going to get S dot, right? Because we're differentiating with respect to t. Okay. What about the right side? Well, I've got the 4 pi out front. What's the derivative of r squared with respect to t? We're going to get 2r times r dot, right? Because there's 2 links in the chain. And so that's what we've got then. So 2 times 4 pi is 8 pi, and there's my r dot. And we're trying to find S dot. So it's already solved for the quantity we're looking for. So I can just directly plug and chug them, right? So we can really combine step 4 here. If I plug in 10 for r and 1 over pi for r dot, I get 80 pi over pi, which is just 80. Okay, what would my units be? This is S dot, so that's going to be ds dt. I need units of surface area over units of time. What would we measure area in terms of? Yeah. It's got to be feet squared because our lengths are in feet, right? So square feet per minute because time is measured in minutes. And that's it. That's the process, right? There's no new calculus there. It's just kind of a cool process that lets you solve some really interesting problems. All right? I'll be done. You can work on stuff. I'll put up an assignment. I'd encourage you to maybe try at least like one introductory problem on the assignment just to make sure you get this thing internalized.